Our next presenter is also ready and will share his work online. We have Dr. Riccardo Togni from DCS Computing, part of the ZeoCat 3D project. We already are connected. A few words about Dr. Togni. He holds a PhD in computational fluid dynamics from University of Bologna and working at DCS Computing, Italy as senior project manager and consultant. His expertise in computational fluid dynamics and DEM, discrete element method modeling, granular flows and reduced order models. He will talk about today he will talk about numerical simulation of the catalytic reactor using a 3D-1D model and focus result on the outcome of simulations performed with different operating temperatures and geometry sizes of the catalyst. Yes, before passing the voice, can you hear us? Is everything?
Yeah.
Is
I
the
can hear
connection
you.
working good?
I can hear you loud and clear.
Thank you, Dr. Riccardo Togni. I will pass the mic to you to talk about the 3D-1D model for the simulation of chemical reactors.
Thank you very much, Valeria, for the introduction, and thank you, everybody, for being here today. It's an honor to present at the end of this ZeoCat project and to see how many good results have been collected. So today I'm going to talk about a novel 3D-1D model for the simulation of catalytic reactors. I'm not the only author of this presentation. Also, Alice Christoph supported me during the entire project. Today I'm going to talk about this new numerical approach for simulating not only methane dehydroaromatization, but in general chemical reaction. And I will describe the modeling approach which has been followed, and in the background also the governing equations that support that, and then we will move to the simulation results and finalize with the conclusions. So we heard during the talks this morning that non-oxidative methane dehydroaromatization, MDA, is very, very important. It's very promising. Despite methane became extremely expensive due to the Ukraine war, but we can still rely on biomethane and develop methods to decompose it into hydrogen and high value aromatics, mainly benzene. So the yield of the reactor, it depends on many different factors. It depends on the operating conditions, for example, the temperature of the gas, but also the concentration of the methane at the inlet, the chemical properties of the catalyst, of course, and the geometry of the catalytic structure. So in this talk, I'm going to focus especially on the effect of the geometry and size on the performance of the catalyst, and how actually can we predict that. We also know that high catalyst porosity involves also a higher surface, more heat exchange, higher reaction rate, and so I get also higher, faster methane reaction. But there are also drawbacks, for example, a difficulty in manufacturing these reactors, but also stronger pressure losses throughout the reactor. So is it possible for us to simulate this process, not only at a small scale, so not only at a centimeter scale, but also up to meter scale for a plant scale reactor? So the project focused mostly on small scale reactors of the order of 10 centimeter length, but since the beginning of the project of this project, we thought of developing a model which is more general, that would allow us to scale up the simulation from centimeter to meter scale. And that's why we developed a hybrid approach, which is a 3D-1D method, which allows us to really span through many different scales. So this method consists of a 3D CFD-DM simulation of some characteristic sections of the reactor. I will describe later on what CFD-DM means. And in between these 3D blocks, this 3D simulation, we have a 1D model, which is basically an advanced interpolation method that allow us to, let's say, propagate the solution and and join together this 3D solution that we get from the CFD-DM method. So this method allows us to simulate the fluid dynamic behavior in such a kind of system, but also investigate the effect of the catalyst structure and operating temperature on the methane conversion and the pressure drop. Here, are we going just to focus on the main reaction of the methane dehydroaromatization, namely the reversible decomposition of methane into benzene into hydrogen. We are well aware that this is not the only reaction happening in such a system. There are many intermediate products and many different reactions, but for the sake of simplicity, we keep it just one reaction. How does it work, this hybrid 3D-1D method? So here, let me choose a different pointer. We see that we discretize our reactor into RVEs, which are relevant volume elements. Each RVE represents a section of the reactor, and each of these RVE are simulated using a CFD, so a computational fluid dynamic DM discrete elements methodology. So CFD allow us to simulate the flow and the chemical reaction around the catalytic structure, and the catalytic structure itself, which in this case is a straight channel configuration, is modeled using particles, namely DM spheres, in the form of fibers. The boundary conditions at the sides of this domain are periodic, so that they allow us to simulate much larger sections of the catalyst, and at the same time keeping the computational cost low. Here we use also an immerse boundary method, which allow us to, let's say, mesh with relatively facility also complex and geometries like the one of the porous structure in the catalyst. So so here we see on the right that we are just focusing on a certain small portion of the reactor, but through the boundary condition, we also actually representing a much larger surrounding area. And in this work, we are focusing on this particular geometry. So it's the straight channel configuration with two fiber diameter size, namely 0.8 and 0.4 millimeters. The 3D model is supported by aspheric software and CFD-DM coupling. They're basically software that we develop at DCS. One is a DM software, and the second one is a CFD-DM coupling software that allow us to solve momentum, energy, and chemical reaction. So here I'm just going through a bit the governing equations. So here in the top right, we have the CFD computational fluid dynamics equations. So the continuity, the Navier-Stokes equation, energy budget, and then we have also here at the bottom the species, the chemical species concentration equation, which consists of a convective transport, a diffusive term, and a source term. Since we are using immerse boundary method, we decompose our entire domain into, let's say, two parts. One part is occupied by the solid structure, and one part is occupied by the fluid. And here on the interface, we impose some proper boundary condition for the fluid and for the temperature, so that we can simulate properly our entire phenomena. So in this next slide, I just focus once again on the chemical species concentration equations. And we see that each one of these equations, so one for methane, hydrogen, and benzene, there is a source term, which on the other hand depends on the molar mass of the chemical species and also on their molar concentrations. We have done this coefficient Kf, Kr, which are the direct and reverse reaction rates, which we can model according to the Arrhenius equation. So it's a very well-known relation that we have used to, let's say, model the chemical reaction. And as I said, we are modeling not just the forward reaction, but also the reverse one, so that the reaction achieves with time a certain chemical equilibrium. And the backward reaction rate is defined like this. So as the ratio between the forward reaction rate and an equilibrium constant. And then, we have also this equilibrium constant that can be expressed as a function of temperature, because we know that the equilibrium of a chemical reaction changes also with the operating temperature. So a lot of parameters that have been calibrated using the support of other consortium partners that provided us with information about the concentration of benzene at equilibrium. And in this way, it was possible for us not only to use data from the literature, but also actively calibrate the Arrhenius coefficients and the equilibrium constant so that we get the desired equilibrium of the reaction. Here we see the simulation result. On the left, we see the velocity field around the catalyst structure. We see that the flow is deviated by the presence of the solid, as it is expected. And here on the right, we see actually benzene concentration increasing at the surface of the catalyst, because this methane dehydroaromatization is triggered basically by the surface contact. So let's move to the first round of results. So we have an effect of the operating temperature on the conversion rate and on also the average velocity of the gas along the reactor. So in this case, I'm just considering 10 centimeter long reactor. The fibers are 4 millimeter in diameter, and the operating temperature in this case are 3, so 873, 923, and 973 Kelvin. We see that for a higher operating temperature, also the equilibrium is shifted towards the products. So we have more benzene. And we see also very interesting that the equilibrium of the reaction is achieved few centimeters after the inlet, and this doesn't seem to be much affected by the operating temperature. We can also get information about the average velocity of the gas along the reactor. This in turn is important to calculate also pressure losses and consequently also the amount of energy required by the pump to keep flow throughout the reactor. So here we see that the higher the temperature, the lower the average, the higher the temperature, the higher the velocity through the reactor. This is a sensible result since the density of the gas decreases with the temperature, and therefore for the same mass flow rate, we get higher velocity through the section of the reactor. Pressure loss is also depicted. Here we see that for the 3 temperature, there is not much difference, but if we zoom in a bit, we see that there is a slight increase in the pressure loss for higher temperatures due to the higher velocity through the reactor. In this case, we kept the operating temperature the same, in this case 873, and we consider the 2 sizes for the fibers, namely 0.4 and 0.8 millimeter. A smaller fiber size contributes to a faster conversion of methane into benzene. And we see here the dashed line, which corresponds to the finer catalyst structure. We see that the equilibrium of the reaction is achieved faster than with bigger fibers. The average velocity, we don't see any big difference between the 2 fiber sizes, but then we have in the average pressure we see that the pressure losses associated to a finer fiber structure are definitely higher. Here, we also investigated the effect of nitrogen content in the inlet of the reactor. So, for example, we see that in the purification process, there might be additional gas species, for example, nitrogen in the feed of the reactor, and we want to investigate actually how these impurities affect the reaction rate. We see that here we have 3 percentages for nitrogen, namely from 5 to 15. 15 is the red line. We see that the conversion rate is lower than with pure methane. And the other important result is also the average velocity. Also in this case, the simulation model is capable to account for different species in the reactor. And we see that the average velocity actually increases because the density of methane is lower than the one of nitrogen, and for the same mass flow we get higher velocities through the reactor. The last investigation that we did using this simulation tool, the catalytic reactor app, is the effect of methane flow rate on the pressure losses. Here we investigated 5 flow rates from 0.1 liters per minute to 2.0 liters per minute. We see that the pressure drop associated to this flow rate is very different, and it increases with the flow rate. And this is allow us also within the simulation framework to estimate the power required by the pump to maintain a certain flow rate inside the reactor. And we see that the power required increases monotonically with the flow rate, but it is still remains of the order of the milliwatt, which is completely negligible if we compare it with the power required for keeping the system at operating temperature, which is of the order of the kilowatt. Conclusions. So during this project, we developed a new 3D-1D model for simulating MDA reactors. So the MD model is model using a simple reversible methane decomposition into hydrogen and benzene, and the reaction rates have been expressed using the Arrhenius equations. This coefficient have been calibrated using literature data, and also by comparing results also with other project partners. So this approach allows us to perform simulation from centimeter line reactor up to 1 meter, because the 3D-1D hybrid approach enables us to simulate very accurately small sections, and then using the 1D model, we can propagate the solution over longer distances, and therefore we keep the computational cost of the entire simulation contained. So this model, although has not been validated directly using experimental results, has been properly calibrated, and it exhibits also sensible results when we, for example, consider the effect of temperature on the conversion rate, but also on the pressure losses, and also the effect of different methane concentration at the inlet on the conversion rate and on the overall gas rate. I want to thank you, everybody, every consortium partners for the fruitful cooperation, and I would be glad to answer to any questions. Thanks.
Thank you very much, Riccardo, Tony. Do we have any questions from our live audience today? Okay, nobody in the room, then I will, I have here a set of questions for you. Actually, there are 2 questions. One of them could be whether the simulation approach could also include other reactions with intermediate products.
Mm-hmm. Yeah, that's a very interesting question. Yeah, the simulation framework using CFD-DM approach can enable also additional reactions. we can build more complex chemical reaction model where we have interconnected chemical reactions where intermediate products are generated. The products then are undergo further reaction until we generate benzene, toluene, and naphthalene. The problem of building such a complex model that is very difficult to calibrate it, because we need also say to find the right parameters of the Arrhenius equation. So for the sake of keeping it simple, we just consider one, but I want to tell you that it can be extended, and the complexity of this reaction chain can be increased.
All right, thank you. The other question would be if it's feasible to apply the app to a different process.
Yeah, it can be adapted also to generic chemical reaction or chemical reactors. For example, we worked on rotary kilns where, for example, carbon particles underwent combustion, or yeah, the range of or calcination. So calcination reactors can also be modeled following this approach. So it's really flexible, and the most important thing is the scalability. So the fact that it can be used effectively at small, so lab scale, up to commercial scales due to this hybrid approach.
Thank you for covering our questions and for sharing your work here today.
Thank you.